In this video, we are going to discuss about Class B amplifiers. There are two types of Class B amplifiers. One is push-pull and another one is complementary symmetry. So here the transistor is biased and the amplitude of the input signal is such a way that the output current flows only for the half cycle of the input signal. So if I plot the graph with respect to IC versus VCE. The Q point will fall below this value. So therefore, the Q point is here. So my output signal is like this. That is half of the input signal, and if you look into the output, so output also, it is only for half cycle you are getting the output, and for remaining half cycle you will not get the output. So this is nothing but your input signal. Okay. So why it is so is the Q point is at the cutoff region. So this line represents the AC load line. So with no input signal, the transistor is biased at the cutoff region, and at this point there is no current flow through the transistor, hence there is no power dissipated by the transistor. However, when the signal is applied, the transistor handles an average current which increase its for larger input signal. So this is contrary to the Class A amplifier, in which the power dissipation is maximum with no input signal and minimum with large input signal. Whereas for the operation of the Class B amplifier, the increase in the transistor dissipation for the increase in the input signal. Since there the average current in the Class B amplifier is less than in Class A, therefore the amount of power dissipated in the transistor is, that is Class B, is very less than Class A. So let us see the circuit diagram of push-pull amplifier. So when during the positive half cycle, this secondary end is positive and this is negative. So this transistor is active and this is inactive. So this is called as push and this is called as pull. So during the negative half cycle, this is negative and this is positive. So this is on and this is off. So this is push and this is pull. Okay. So thereby the current flowing through the output is always in the opposite direction, right? So during the negative half cycle also you are getting the output, and during the positive half cycle also you are getting the output. So this type of output signal will give a large distortion. So in order to avoid this, we use two transistor which is connected in the push-pull arrangement. So the one transistor will conduct in the one half cycle and the another will conduct in the another half cycle, so which will reduces the distortion, and it also increases the efficiency. So here I can I have taken two identical transistor, that is Q1 and Q2, and the two transformers, that is it is nothing but a center tap transformer T1 and T2. So the input transformer is called as a phase shifter, phase splitter, in order to produce this two signal voltage, which is 180 degree phase shift, in order to drive the transistor Q1 and Q2. So this transistor transformer is an output transformer. T2 is an output transformer, which is required to couple the AC output signal from the collector to the load. So here the transistor Q1 and Q2 is are biased at cutoff, which is done by providing a zero bias on the base of the each transistor. So this zero bias is achieved by connecting the emitter and base terminal together. Of the each transistor. So you can see the base and the emitter is connected together. Thereby we can achieve a zero bias. So in order to get a balanced circuit, the two emitters are connected to the center tap of the transformer 1 of the secondary and VCC. Okay. So when there is no input signal, both the transistor Q1 and Q2 are in cutoff, hence there is no current drawn from the VCC. So thus there is no power is wasted on standby, therefore the power dissipation in both transistors is 0. So even if both the transistor Q1 and Q2 are biased little above the cutoff points, the transformer still operate in the zero flux. It is because that the fact that the DC bias current for each transistor will flow in the opposite direction through the secondary transformer of T2. So the magnetic flux which is set up by each of this current which will result in the opposite flux through the magnetic core. So the net flux in the perfectly matched case is 0. So thus the transformer is not required to handle a large flux due to DC bias current. As a result, the transformer have a small size of core bias to operate near zero flux. So during the positive half cycle of the input signal, this Q1 is positive and Q2 is negative. So since the Q1 conducts while the Q2 is off, so when the input signal goes negative, Q1 turns off and Q2 conduct. At this instant, only one transistor is conducting. So each transistor handle the one half of the input signal. Then the output transformer joins these two half values and produces a full wave sign at the load resistor. So it is found that joining the two output of the transistor, it will not be very perfect, therefore the output get distorted. So this class B push-pull amplifier is also called as double-ended class B amplifier. So this amplifier is usually employed in the final stage of the amplifier. and it is used in the public address systems like tape recorders and stereo amplifiers. So you can see the efficiency of the advantages of class B amplifiers. It has very less harmonic distortion for a given power output because of the absence of the even harmonic, and the effects of the ripple voltage contained in the power supply will be balanced out, and the efficiency is around 78.5, which is very much higher than the class A amplifier, which is 25%, and we can achieve the impedance matching since we are employed a transformer at the output. But you can see the disadvantage. It is bulky and expensive, and it requires a two out of phase input signal in order to operate and it also necessitates input center tapped transformers, and the transformers which we have used will produce a magnetic field which causes a distortion of the output. Since the transformer is biased at cutoff, it means the DC bias voltage is 0. So whenever the input voltage exceed the VBE before the transistor conducts, so the transistor will not be conduct until the voltage exceed 0.7. Okay, this is 0.7, this is the minus 0.7 for silicon and 0.3 for germanium. So because of this, there is a time interval between the positive and negative alternation of the input signal when neither the transistor is conducting. So you will get the output. So till this one you will not get any output. So if this is 5 and this is minus 5, you will get 4.3 and minus 4.3. So this distortion is called as crossover distortion. So this crossover distortion may be avoided by applying a slight forward bias of 0.7 to the base emitter junction of the both transistor of the amplifier circuit. So this will cause the transistor to conduct immediately when the AC signal is applied. So this application of the slight forward bias shift the Q point which is above the cutoff in such state each transistor operate for more than 1/2 cycle, and the resulting operation is called as class AB operation. So next let us calculate the efficiency of the class B push-pull amplifier. So we know that IC is equal to AC is AC current, that is equal to IQ. IQ is nothing but DC value of the output current of Q1 or Q2 transistor, and B0 plus B1 cos omega t plus B2 cos 2 omega t and B3 cos 3 omega t, and it will goes on, right? So likewise I can write it for the next signal IC2. So IC2 I can write it as IQ plus B0 minus B1 cos omega t, because this is 180 degree phase shift. IC1 is produced from the transistor T1 and IC2 is produced by the transistor T2, and it will have a 180 degree phase shift. So cos omega t plus phi is nothing but minus cos omega t. So that is why I have written minus B1 cos omega t plus B2 cos 2 omega t plus phi plus B3 cos 3 omega t plus phi. So 2 phi is nothing but 0, so you will get 2 omega t, and this is nothing but minus B3 cos omega t. So if I subtract the third and fourth equation, I will get 2b1 cos omega t plus 2b3 cos omega 3 omega t. So you can see the even harmonics get cancelled out. So the third harmonic is a principal source of distortion provided that the two transistors should be identical. So I can write IC is equal to 2 B1 cos omega t plus B3 cos omega 3 omega t. So next I need to find the value of efficiency. So I can write DC power dissipation is equal to I average into VCC. I average I can write as 2Im divided by pi. So you substitute here, you will get PDC equal to 2Im VCC divided by pi. Vm I can write it, Im I can write it as Vm by RL. For PAC is nothing but VRMS into IRMS. So that is equal to VRMS square divided by RL, because IRMS I can write it as VRMS by RL. VRMS I can write it as Vm by root 2. So if I solve, I will get Vm square divided by 2RL. So you have to divide in order to find the efficiency. Efficiency is equal to PAC divided by PDC. So you substitute Vm square divided by 2RL divided by 2 Vm VCC divided by pi RL. So Vm get cancelled, you will get Vm pi divided by 4 VCC. So if you see the diagram, here this is nothing but your VCC, and this value is nothing but Vm. Okay, so I can write Vm is equal to VCC. So therefore I can write Vm is equal to VCC. So you substitute here. So Vm VCC will get cancelled out. So pi divided by 4 into 100. So pi divided by 4 into 100 is 78.5. So this is the efficiency of class B push-pull amplifier. Thank you.